Hello everyone, welcome to my YouTube channel. In my last video, I have discussed about the matrix representation of a linear transformation. Today I will discuss about invertible linear transformation. So the definition of invertible linear transformation is as follows. Let T be a transformation from U to V such that T is 1, 1 and onto. Then T is called invertible linear transformation. So if T is 1, 1, what are the conditions that it holds? If T is 1, 1, then for two different elements of the vector space U, there must have two distinct images. That is, if alpha 1, alpha 2 belongs to U and alpha 1 is not equal to alpha 2, then T of alpha 1, that is the image of alpha 1 under the transformation T, is not equal to image of alpha 2 under the transformation T. So if this condition holds, then we call T is 1, 1, or if you have two elements alpha 1 and alpha 2 such that alpha 1 is equal to alpha 2, then their images must be same. So in other words, T is 1, 1 if alpha 1 alpha 2 belongs to U and alpha 1 equal to alpha 2. This implies T of alpha 1 is equals to T of alpha 2. So this was the definition of 1, 1 transformation. Now if we want to check onto, then for each element in the vector space, in the second vector space V, there should be a pre-image in the vector space U. So T is set to be onto if for all beta belongs to V, there exists alpha belongs to U such that T of alpha equal to beta. So if this condition hold, we say that T is onto. Now if we see that T is 1, 1 and onto both, then we can say that T is an invertible linear transformation. So if T is 1, 1 and onto, we define a function from V to U. This time we are reversing the vector spaces, that is, we are defining the transformation from V to U called the inverse of T. Since transformation is invertible, so inverse exists, so this is called inverse of T and this is denoted by T inverse. And remember, this T inverse will also be 1, 1 and onto, because the transformation that we have taken was 1, 1 and onto, so the inverse that is obtained by the transformation will always be 1, 1 and onto. So now I am going to take one example based on the invertible linear transformation. So the example is as follows. Let T be a linear operator. This is linear operator, that is the transformation defined on R cube to R cube. Defined by T of x1, x2, x3 is equals to 3x1 plus x3, minus 2x1 plus x2, minus x1 plus 2x2 plus 4x3. We have to prove that T is an invertible transformation and we have to find the formula for the T inverse. So firstly we will try to find out the transformation matrix. So the transformation is given from R cube into R cube. Since it is talking about R cube, so we have a standard basis, because basis is not given in the question, so we will always take standard basis, that is 1, 0, 0, 0, 1, 0, 0, 0, 1. Now we have this standard basis and we have to apply the elements of the basis over the given transformation. So the transformation is given T of x1, x2, x3 is equals to 3x1 plus x3, minus 2x1 plus x2, minus x1 plus 2x2 plus 4x3. Now this was the given transformation. If we apply the definition, this becomes T of 1, 0, 0, because we have taken the first element of the basis, and this will be written as 3, -2, -1. And if we express it, we can express it in the linear combination of the elements of the basis of R cube, because both spaces are same, so we have to express these elements in the linear combination of the elements of the basis. So we can write it as 3, 1, 0, 0 plus -2, 0, 1, 0 plus -1, 0, 0, 1. Whenever you have given a standard basis, you can directly take it as a scalar in the column of the transformation matrix. So I will write other vectors directly, that is t 0, 1, 0 equal to, if we put, then this can be written as 0 because there is no x2. Here we get 1 and here we get 2. And if you express, this can be written as 0, 1, 0, 0 plus 1, 0, 1, 0 plus 2, 0, 0, 1. So that's the way in which we can write, we can express this vector. Now if we take our last vector of the basis, then this can be expressed as t 0, 0, 1. If we put it into the given transformation, this can be expressed as 1, 0, 4. So these are the vectors, and if we express in the form of linear combination of the basis elements, this can be written as 1, 1, 0, 0 plus 0, 0, 1, 0 plus 4, 0, 0, 1. Now this is the expression for the transformation in the linear combination of the elements of basis. Now if we write the transformation matrix related to the basis B, this can be written as, this is a 3 cross 3 matrix since both the spaces were same, and now we will put the scalars in the form of columns, that is 3, -2, -1, and the next column will be 0, 1, 2, other column will be 1, 0, 4. Since it was given that the transformation was invertible, and it is not given, we have to prove that it is invertible. So how we can prove that the given matrix is invertible? I will discuss it in when I will teach you about the matrices, but before that I want to tell you that a matrix is said to be invertible if its determinant is non-zero. So in order to check that this transformation is invertible or not, we just check the transformation matrix determinant. If it is non-zero, we say that transformation is invertible. So let's check out the determinant of this matrix. If I name it A, then the determinant of A equal to, we just check out simply, this column will be hidden, this becomes 4 minus 0 plus 0, so this term will not be here, plus 1 minus 4 plus 1. After simplifying, we get 9. The determinant is 9, that is a non-zero value. So from here we can say that the transformation T is invertible, and if it is invertible, we can find out the inverse for this transformation. Now in order to find the inverse, T inverse, we have to take the inverse of the matrix T, and we know that we have so many methods to find out the inverse of a matrix, that is the cofactor method and so on. So I am not going to discuss that. I am writing directly the inverse of the transformation, and that is as follows. We know that whenever we have to find the inverse of a matrix, we write A inverse is equals to adjoint of A divided by determinant of A. So the same method we will apply here. The cofactor matrix that is obtained here, I am writing it directly. You can find out it by yourself because this is very easy. You just find out the cofactors and then make a new matrix that is called cofactor matrix and divide it by determinant. You will get T inverse. So I am writing it directly. 4, 8 minus 3 and 2, 13 minus 6 minus 1 minus 2, 3. So this is the cofactor matrix. We have to find the formula for T inverse. In order to find the formula, we have to multiply this T inverse by a vector A B, C. Then we get a new transformation. So if I multiply, this is also taken over the basis B. So I am writing it like this, T inverse over B. Now if I multiply it with this vector, then this can be written as 1 by 9, 4, 2, minus 1, 8, 13, minus 2, minus 3, minus 6, 3, multiplied with A, B, C. Now 1 by 9 will be outside. I am just multiplying the rows and columns. So this becomes 4A plus 2B minus C, and this becomes 8A plus 13B minus 2C, and this becomes minus 3A minus 6B plus 3C. So this was the way in which we can find the formula for the T inverse also. So the formula for T inverse related to the same basis B is as follows. If I name this vector as alpha, then this can be written as T inverse of alpha equal to T inverse of A, B, C. If this is a row vector, this was a column vector, that's why we are getting a column vector here. But if I express it in the form of row, this can be expressed as 1 by 9, 4A plus 2B minus C, comma 8A plus 13B minus 2C, comma minus 3A minus 6B plus 3C. So this was the formula for T inverse, and in this way we can find the invertible linear transformation or the inverse of the transformation matrix. So I hope all of you are getting my point. So if you are liking my content, please subscribe my channel. Thank you.